Hello, in this video we're going to look at estimating the value of a function using linear approximation. Now linear approximation kind of falls under the general heading of using differentials, and it's this calculus idea where we work with the derivative and approximate values with the derivative. So the idea here is I have 1.98 to the fourth power, and we're going to try and estimate that value. Now, of course, you can plug it in the calculator, but we're going to use this calculus technique to help practice some of that calculus. So 1.98. I go to my curve here. I recognize that I have this curve y equals x to the fourth because I'm finding 1.98 to the fourth power. So the function I'm dealing with is x to the fourth. And I go to 1.98 and I'm like, what is the value there? What is that y value? Well, I don't know that, but I do know what it is 2 to the fourth. I know that 2 to the fourth, if I go to the curve, the y value is 16. Okay, I know that one. I can easily figure that out. The idea is, if I go to this and I make a linear approximation, so I create a tangent line going through 16, I can use that tangent line to approximate the value at 1.98 because I find it on the line. And then I say, hey, that's the y value, because it's only that much different between the actual and estimated y value. Sure, it's not exact, but it's a good approximation. Now, of course, I can only do that close to points around 1.98, because if I use the approximation up here to approximate, x equals 1, well, now I'm pretty far off the curve. So when I do this approximation, the point where I create my tangent line has to be relatively close to the value I'm estimating. I create a tangent line at a point close to the value I'm trying to estimate. So in this case, at 2. Now, the equation of a tangent line. Well, it's the equation of a line, so we go y minus y sub 1 equals m times x minus x sub 1. But I'm going to take that and I'm going to make it a little more calculus-y. We're going to use L of x is equal to, and L because linear approximation. What is m? M is the slope, which means it's the derivative, f prime, and it's the slope specifically at x equals 2 there, that specific point. So we're going to say c. C is the closest point to where we are trying to estimate, the closest known point to where we are trying to estimate. So it's f prime of c times x minus, well, at which x value am I creating this line? At 2, which is my c value, the closest known point. And then we're going to move this y sub 1 over to this side, and we're going to add it, so plus y sub 1, which means plus f of c. That's plus this, that's y sub 1, or f of c. That's the y value at that c point. So this gives me a little equation of a tangent line, and we're going to use this to approximate the value at 1.98. So I'm going to create the equation of this line at 2, and then I'll plug in 1.98 for x to do the estimating. All right, let's slide over to estimate 1.98 to the fourth. I identify the type of function that is at work here, and it's x to the fourth. Okay, that's my function. Now I need to know the derivative, so I'm going to find f prime of x, that's 4x to the third. But I'm creating my tangent line at x equals, or we can say c equals 2, because that's the closest known point. I'm trying to estimate 1.98, but 2 is the closest value that I just easily know the value of it. So I now find f prime of 2, which is 4 times 8, which gives me 32. So I found my f prime of c. So I have L of x is equal to 32 times x minus 2, because that's where I'm approximating at, plus f of c. So that's the original function evaluated at 2. So we go f of 2, which is 2 to the fourth, which is 16. So it's plus 16. Now that right there is the linear approximation at 2. But what's the whole reason that we created that? to figure out what the value is at 1.98. So we go L of 1.98, which is equal to 32 times 1.98 minus 2 plus 16. So we go through and we can simplify this. 32 times negative 0.02 plus 16. And that gives me 15.36 after I do a little bit of simplifying work there. So that's the approximated value. Now for purposes here, we're going to look at the actual value and kind of compare these two things. So if I were to go and use my calculator and find f of 1.98, so that means 1.98 to the fourth power, what would I get? Actually, something very close. I get 15.36953616. So very, very similar. So what this is saying is that point on a curve, 1.98, that's at 15.3695, But then when I use my tangent line, when I get the y value right here, I get 15.36. So it's just barely below it. But see, it's a good approximation. It's a little bit below, but it's very close. And in fact, how close is it? Well, we can look at our relative error. And that's that percentage. How much am I off? And relative error is the absolute value of the actual minus the estimated divided by the actual. So 15.369.53616 minus 15.36, and the absolute value of that divided by the actual. So we'll run that string of decimals again, 369.53616, and then we multiply by 100 to make it a percentage. And in the end, that's going to equal 0.062%. So we're only off by 0.06%, which is great. That's a really good approximation there. Estimate 1.98 to the fourth. It's 15.36, which is a 0.062% relative error. Run through that one more time. To estimate with a linear approximation, you identify the type of function you are dealing with. You're going to take the derivative and evaluate the derivative at the closest point you know. Kind of know off the top of your head, mental math. You create the linear approximation, the equation of the tangent line. So it's got a fancy word, linear approximation, but it's just an equation of a tangent line. And then you evaluate the tangent line at the point you're trying to estimate, and you find that answer. And there's your approximation.